And hello everyone, welcome to section 6.2, which is just going to be an extension on section 6.1 basically. So we're going to talk about solving more trigonometric equations. These will be equations that need a little bit different techniques than 6.1, whereas 6.1 was maybe they were a little more straightforward. We kind of just jumped to the unit circle and see what those values were. Here we have to do some nicer algebraic tricks right off the bat, just to get to a point where we can finally go to the unit circle and pick up some sort of value. So a little bit trickier, not a lot trickier, but yeah, a little bit trickier. So just want to roll through a couple of examples. I've got 6 of them picked out that I want to do, and they're all just a little bit different than they were in 6.1. So we'll take a look and see. First things first, let's stick to between 0 and 360 and 0 and 2 pi. Well, I say 0 degrees and 360 degrees. That way we can just get used to solving these types of equations without having to do the whole plus 2 pi k for any integer k. Let's stick to one trick within the unit circle just to get these solutions out there. And then we can always extend that concept, a little bit later, like in the next section, 6.3, we can always extend that out. But let's focus on just getting the solutions with one trip around the unit circle. So first things first, let's say we want to solve the equation for theta between 0 and 360 degrees. And if we get to 360, we'll stop because that was 0. And let's pick on something that has the form square root of 3 times secant of theta equals 2. Let's say we're handed an equation like this. Right off the bat, a little different. It's got a secant of theta. So right off the bat, we're going to take both sides, isolate secant by first dividing both sides by the square root of 3. So I can get those to cancel out. So I want to know where secant of theta is 2 over root 3. Remember, secant of theta is actually the reciprocal of cosine of theta. So this is 1 over cosine of theta is 2 over root 3. Which means I'm really looking for the reciprocal here. I want to know where cosine of theta is root 3 over 2. So you can cross multiply and isolate cosine again, or you can just say that if these are the same value, then their reciprocals are the same value. So cosine of theta has to equal root 3 over 2. So again, I go to my unit circle, and I want to try and pick up where cosine of theta is going to be root 3 over 2. Well, it's positive, so it's going to happen here. And again, we're sticking between 0 degrees and 360 degrees. So I'm going to use degrees and say that this happens when theta is equal to 30 degrees. I get a positive root 3 over 2. But cosine is also positive down in quadrant 4. So it'll happen again when theta is equal to 330 degrees. So my reference angle is 30 degrees. I put that down into quadrant 4 to pick up the other one. I don't want anything in quadrant 2 or quadrant 3 for theta, because then a cosine of theta would be spitting out a negative value, and that is definitely not the case here. It's a positive value. So these would be my 2 solutions. And again, I'm just sticking to one trip around the unit circle. Thus, theta equals 30 degrees and 330 degrees. So you can see right off the bat, not too terrible. Right, so you get just 2 nice answers. Again, we're sticking one trip around the unit circle, so we don't have to bring in the whole plus 360k to pick up more and more and more. They're telling us to stay between 0 degrees and 360 degrees, so we're done. So a little different because it had a secant function in there, but again, nothing too scary. If we look at something that is a little different, let's say we have an equation of the form sine of 2 theta minus cosine of theta is equal to 0. Let's say we have an equation that's in this form. Now, right off the bat, ew, double angle, right? So what we want to do is rewrite this double angle so that we're always solving for theta. I don't want to solve for theta while simultaneously solving for twice theta. Right? There's too much going on there. So we can rewrite this sine of 2 theta, and I've got the formulas pulled up on the screen. This is a double angle formula for the sine function. So it's going to be 2 sine of theta cosine theta minus this cosine theta is still there equals 0. So I simply rewrite this first piece using my nice double angle formula for sine of theta, for sine of 2 theta. So now we can work through this, and notice there's a common factor, cosine of theta. Again, it's still a mixture of 2 different trig functions, which is tough, but at least now they're all focused on theta. I'm going to use this greatest common factor, cosine of theta, to factor the left-hand side into cosine of theta times 2 sine of theta. I still need a minus 1 as a placeholder here. So again, if I were to redistribute that cosine of theta, the left-hand side stays the same. Nothing has changed. But again, in algebra, we always wanted these things factored so we could set each factor equal to 0. We're doing that same thing here. We're going to set each factor equal to 0. By that, I mean either cosine of theta is 0, or 2 times sine of theta minus 1 is 0. 2 things being multiplied, getting a result of 0. So I just set each one of those factors equal to 0. Well, again, back to our unit circle here. We want to know where cosine of theta is going to be 0. And again, we're talking about degrees, just staying within 1 trip around the unit circle. So that's going to be up here at 90 degrees and down here at 270 degrees. That's where I'm going to have an x value of 0. It's not going to the left or going to the right at all. I'll pick up 0 for my cosine. Here I'm going to add 1 and divide by 2 to get sine of theta has to equal 1/2. So again, I jump to my unit circle and I just find out where sine of theta is going to be 1/2. Again, we're talking about degrees. We want sine of theta to be a positive 1/2 value. So that's going to happen over here at 30 degrees. And it's going to happen over here at 180 minus 30, which is 150 degrees. So you can see that I'm picking up different solutions from each one of these, but they're all going to be the same solution because I would definitely get a 0 for cosine, which would make everything on the left 0, solving my equation. Or if I focus on theta being one of these angles, then when I plug it into this sine function here, and then double it and subtract 1, I'll get 0, making the left-hand side 0 and the right-hand side 0. So I'm picking up a lot more solutions. The reason I'm picking up a lot more solutions is because of that double angle. I'll pick up more solutions when the bigger or the larger the multiple gets. We'll see that in 6.3 quite a lot. Thus, theta is equal to, and we'll put them in order, 30 degrees, 90 degrees, 150 degrees, 270 degrees. You wouldn't be wrong if you didn't put them in order, right? There's nothing saying you have to put them in order, but it just looks a little better. So that one had something a little different to it. That one had a double angle. We didn't see that in 6.1, but we know how to handle double angles, and that's always just a great way to look at these equations, especially at first when you're new to them and you haven't been exposed to them quite a lot. If you see a double angle, that's a big red flag to tell you need to use a double angle formula. If you see a half angle, that should be a big red flag that says you need to use a half angle formula. So when you see that type of stuff pop up, you should be going to that formula sheet and looking for those formulas and breaking them up, be it a double angle or a half angle or whatever you see yourself staring at, product to sum, sum to product. That's a big red flag that says, hey, use me. There's a reason we have this formula, so let's use it. Let's do another one that has us using theta between 0 and 360 degrees. So, same thing, solve the equation, sticking to 1 trip around the unit circle. Let's say we're given something that looks like 2 times sine of theta minus 1 is equal to cosecant of theta. Okay, again, looking a little trickier because this one's got a mixture of sine of theta on one side. The other side's not 0 or something simple like that. It's actually a whole other trig function, cosecant of theta. But again, just remember that cosecant of theta is the reciprocal of sine of theta. And that should lead you to try something like rewriting it first as 1 over sine of theta on the right-hand side. And again, we don't really like to mess with denominators, right? Denominators they make stuff a little trickier. So I can multiply both sides by sine of theta. And when I do that, I will cancel out the right-hand side, not completely, it's not going to be 0, right? That ratio is still 1. I'm multiplying by sine of theta, and then I'm dividing by sine of theta. So that ratio still spits out 1. But look at the left-hand side now. I have sine of theta times 2 sine theta minus 1. But I'm not getting a result of 0. So I can't set each one of these equal to 0. And it also doesn't work for 1. I can't set each one of these equal to 1 and say that the product is always going to be 1. So what I need to do is actually multiply this out to get 2 sine squared of theta minus sine of theta is equal to 1. Now, that sine squared of theta, that should kind of get your brain thinking, oh, this is like one of those quadratic style of equations where if I get everything on one side set equal to 0, I might be able to factor it. And indeed, that's what we're going to do. I'm going to look at 2 sine squared of theta minus sine of theta minus 1 equals 0. So I'll subtract 1 on both sides to get the right-hand side set equal to 0. Now we can try and factor this thing and set each factor equal to 0. Again, we love that 0 product property specifically for that reason. Well, let's start off by saying, maybe here we'll put 2 sine of theta. Here's sine of theta. I want to get a negative sine of theta, so I'm going to do a minus 1 and a plus 1. And again, just a reminder, a quick check to make sure you got the right factors. Your 2 inner terms multiplied together combined with your 2 outer terms multiplied together, negative 2 sine of theta, should combine to give you negative sine of theta. And they do, so we've got the correct factors, which means we're good to move forward. How do we move forward? We write this factor, 2 sine of theta plus 1 is 0, or this factor, sine of theta minus 1 is 0. And I'm getting a result of 0 when I multiply these 2 factors. So either one of those factors could be equal to 0, and I'll pick up a really nice solution. Subtract 1 and divide by 2. This one is telling me to go find where sine of theta equals negative 1/2. Again, I just rely on my unit circle to tell me this is a negative 1/2, so I want to be down here in quadrants 3 and 4, right? Sine function is going to be negative in quadrant 3 and quadrant 4. It's picking up those negative y values. So I want to look at 180 plus 30, which is 210 degrees, and 360 minus 30, which is 330 degrees. That's where my y values will be negative 1/2. This one, I add 1 on both sides. It just tells me to find on the unit circle where sine of theta is positive 1. That's going to be up here at 90 degrees. So there are my 3 solutions. And now I found where I can have theta. It can be, and again, I'll just put them in order. 90 degrees, 210 degrees, and we'll squeeze 330 degrees right down there. So those are all my choices for theta. So you can see again, 6.2 is going to need a couple little more algebraic tricks. Practice all the ones in 6.1 first, because in 6.2 we're going to need to start using some other tricks. Right now, this one I didn't need like a double angle or a half angle formula, but I really needed to rely on that reciprocal and multiply both sides by sine of theta, which you might not intuitively do the first time you come across a problem like this. Right? But when you see these reciprocal functions, that's a really nice way of getting rid of them so that you don't have to deal with the reciprocal functions, right? You can just deal with, only sine or only cosine. Same thing works for tangent. If you see the tangent function, which is the ratio of sine over cosine, you can multiply both sides by cosine everywhere to get that denominator to cancel out, shifting you into just looking at maybe the sine function instead. Right, so these are all tricks you'll have to try and just start getting comfortable with. Let's switch this up to radian now. Let's say we want to solve each equation when it's between 0 and 2 pi. And again, giving exact values. We don't want a bunch of weird decimal approximations. So we're hunting for those exact values. Let's say we have something that looks like cosine of x minus cosine of 2x. It is equal to 0. All right, so again, be careful. This argument, cosine of x, only has that single angle. Oh, sorry, not x, I meant theta. All right, we're talking theta here. I defaulted back to x because that's what the book had. So we're talking about theta here. Again, one is just an angle theta, the other is a double angle. So this is a big red flag that says, hey, you should probably go find a nice double angle formula. Now, the ones that I have on the screen, for cosine 2 theta, you can see there's a couple choices that you can deal with when you talk about cosine 2 theta. If you look at each one of those choices, notice the first one has a mixture of both cosine and sine. Squared, actually. So you're going to have cosine squared theta minus sine squared of theta to replace here. Then you also have a cosine of theta. Now you're dealing with a cosine function being squared and a sine function being squared. That's 3 different things you have to account for, and that could be tricky. The second one has 2 cosine squared theta minus 1. That means you'll have to deal with a cosine squared. And if you look back at our original problem, the cosine function, that's not going to go anywhere. That seems a little easier, right? Gets rid of the sine squared business. And if you look at the third one, it does have sine squared of theta in it, which means I'd have to still deal with cosine of theta and then some other sine squared of theta. Again, that mixture is 2 different trig functions. So it takes practice, but the good one to use is the second one. The best one, or maybe it's more an opinion, you could use any one of the 3 and it would eventually get you to the right answer. But maybe my gut instinct would be to go and use the second one, 2 cosine squared of theta minus 1, to replace cosine 2 theta. If you use that second one, you do not have to deal with a sine function at all, which in my eyes, again, just kind of speeds up the process. You could use any one of those 3 and still eventually get to the right answer, but you'd have to really fight with this extra sine function in order to get there. So I think this is the fastest way. Looking at it, it now kind of reveals itself because of that cosine squared as one of those functions that I probably have to play around with that square to see if I can get it to factor. First, don't forget to distribute that negative everywhere. And I'm going to rewrite it so I see the square piece sitting up front. Negative 2 cosine squared of theta plus cosine of theta plus 1 equals 0. Now the negative is kind of just odd. I don't really like the negative sitting there. So I'll multiply both sides by a negative 1. That'll get me to negative is positive 2 cosine squared of theta minus cosine of theta. minus 1, negative 0, that's just silly, that's still 0. So, and now it looks exactly like the other stuff we just factored. And it looks like I can factor this down into 2 cosine theta minus 1 times 2, or sorry, plus 1 times cosine theta minus 1. I switched the plus and the minus because, again, I want a negative cosine theta. So this will give me negative 2 cosine theta from my outer terms, positive 1 cosine theta from my inner terms. That's definitely leaving me behind a negative cosine of theta. So make sure you get those signs, S-I-G-N signs, correct inside those factors. You know what to do from here, right? Set each one of these factors equal to 0. So each factor gets set equal to 0. Subtract 1, divide by 2. Where is cosine of theta equal to negative 1/2? We jump towards our unit circle. Cosine needs to be negative, so I need to be in quadrant 2 and in quadrant 3. And I want it to be negative 1/2. So I'm up here at 90 plus 30, which is 120 degrees. And then I'm down here at 180 plus 60 degrees, which will give me 240 degrees. All right, cosine's negative 1/2. We're in radian mode. Let's not forget, I switched it up on us. I said, let's put it in radian mode. Right? So that means each one of these, I need to shift it a little bit. There we go. Clean that up. Oh, I could have left that there. So again, now we need to go back over into quadrant 2 to pick up cosine to be negative 1/2. So that's going to happen at 2 pi over 3. And then down here at 4 pi over 3. And then this one, we need cosine of theta to equal positive 1. So I'm going to look over here. Cosine's positive 1 at 0 radian. That's the only place it's positive 1. So theta is going to be 0, 2 pi over 3, or 4 pi over 3. Those are our solutions, staying within that one trip around the unit circle. So again, sometimes we need to use these formulas to break things up and make them a little nicer. Sometimes we have choices. I say sometimes, usually it's for that cosine 2 theta, right? We have 3 choices that we can make. Give one a try, right? Just give one of the 3 a try and see where it gets you. And if you feel yourself coming to a dead end, maybe back it up and try a different one. Right? But ultimately, all 3 of those will eventually lead you down the right path. It's just one path might be slightly longer than the other path. Right? So we just have to be careful about that. Okay, let's do another one. Let's pick on, still staying between 0 and 2 pi. Let's pick on something that looks like 4 sine squared theta plus 4 cosine theta minus 5 equals 0. And again, it looks real tempting to jump right into it and try and factor it, but this is a sine, this is a cosine. By jumping right into it and trying to factor it with a sine and a sine, then your inner outer terms are going to give you some weird sort of sine function, not the cosine function. So it's close, but it's not exactly what we need to do right now. We don't need to jump into the factoring because it's not going to lead us anywhere. What we need to do is rewrite this sine squared as something involving cosine of theta. So don't worry so much about the 4 in front of the sine squared of theta. What you want to do is jump to your really old Pythagorean identity. Sine squared is 1 minus cosine squared. Right? And I've got it all the way up there. It's not exactly explicitly solved for sine squared of theta, but if we subtract cosine squared of theta on both sides, we can pick up that nice identity that says I'm rewriting sine squared of theta as 1 minus cosine squared of theta. Now I do have this multiple of 4 sitting out front, but I'm a lot better off now because 4 minus 4 cosine squared of theta plus 4 cosine theta minus 5 equals 0 does really have that quadratic feel to it where I'm squaring the cosine function and then this just is the cosine function. And I'll pick up a new constant on the end. So it does still have that old feel that we had in the last couple problems. So I'll rewrite it so it's negative 4 cosine squared of theta plus 4 cosine theta. Positive 4, negative 5 is negative 1. The right-hand side is still 0. Again, I just don't like this like negative leading coefficient, so I think I'm going to multiply both sides by a negative 1, which just changes all my signs. And of course, the right-hand side is still 0. Right, here's a negative, and we'll just clean this up. So it just switches all my signs. Yeah, we multiply a negative over here, but that's just 0. Again, it just helps us to maybe factor it a little nicer. So I want 4 cosine squared of theta. I'm going to do 2 cosine theta, 2 cosine theta. I want a positive 1 on the end. So I'm going to give a negative 1 and a negative 1 inside each of those factors. Now look at these factors. Right, yeah, I'm definitely getting 4 cosine squared of theta from the first times the first. I'm subtracting 2 cosine theta, subtracting 2 cosine theta. Yeah, that's negative 4 cosine of thetas. And then negative 1 times negative 1 is still positive 1 on the end. So I have picked up the correct factors. In fact, these FOIL back out to this expression. And this expression must factor this way. But they're the same. So really, I don't need to do the same work twice. I just need to figure out, hey, where is 2 cosine theta minus 1, 0? And then I repeat that process, but there's no reason to do it twice. So I add 1 and divide by 2 to get cosine of theta equals positive 1/2. But I need to know theta. I need to solve this and see what theta is. So again, back to that unit circle. We want positive 1/2. Cosine is positive in quadrants 1 and 4. It's going to be positive 1/2. Again, we're talking radian, so it's going to be at pi over 3. And it's also going to be down here at 5 pi over 3. So my unit circle tells me theta is 5 pi over, pi over 3 or 5 pi over 3, if I put them in order. So we pick up 2 nice solutions. So again, it's all about looking at this mixture of sine and cosine and trying to get it boiled back down into just one trig function, which you can't always do, but man, it makes things a lot easier. So let's pick on one more. This one's going to have a half angle in it. So I'm looking at sine of theta over 2. There's my half angle. Minus cosine of theta is equal to 0. Let me put that on the screen for you. There you go. So this half angle formula, there's a big red flag saying, hey, I should probably use that sine theta over 2 formula. I should probably look at that and actually write sine theta over 2 as, now be careful, there's a plus or minus here, right? We're not exactly sure which one. Theta is somewhere between 0 and 2 pi, which means quadrant 1, 2, 3, 4. So I don't know positive or negative just yet. So you do have to trust that formula and make sure you write it out so that you get the plus or the minus, because we're not sure which one it is yet. So this looks kind of weird. Again, the nice thing to do here would be, since we're dealing with a square root, go back to our old algebra tricks. When we saw a function that had a radical in it, we liked to isolate that radical and square both sides of the equation. What I mean isolate the radical, I mean just get the radical alone by itself on one side, and then you square both sides of the equation to get rid of the radical. And this is a process that if there are multiple radicals, you might need to repeat a couple times to get the radicals to go away, but eventually you can get those radicals to go away. But remember that when we did that, we may have picked up some erroneous solutions. If we square both sides, we're ignoring the fact that one side might be negative while the other side's positive. So when you do this process, and here's how I'm going to start, I'm going to isolate the radical, just like we did back in college algebra, which means I have plus or minus, right? I still don't know which one it is, of the square root of 1 minus cosine theta over 2 must be equal to, this is cosine theta, I added it over to the other side. I've isolated this radical so that now I can square both sides of the equation. I square the left-hand side, which means I also square the right-hand side, so that I can keep my equality. But when I square a positive, I get a positive. When I square a negative, I get a positive. So no matter what, this left-hand side, when I square it out, it's going to cancel out the radical, and it's definitely going to be positive because a square is always positive. You know, unless you're talking about 0, then it's still just 0. Still don't use the negative. And this I'm going to rewrite in the notation cosine squared of theta. So this gives me something that doesn't have a radical, which is a lot nicer. But again, at this point, I have squared both sides. I need to remember to go back and check my answers. I may be picking up an erroneous answer at this point. But let's just get it solved for now. So dealing with what we have, I'm going to multiply both sides by 2 to get that out of the way. I don't want to see that fraction while I'm trying to solve here. So here's the equation I'm looking at. 1 minus cosine theta equals 2 cosine squared of theta. There's still a square there. There's a cosine there. So I'm going to get this thing set equal to 0 by adding a cosine of theta and subtracting a 1 on both sides. Now, it doesn't matter if you get 0 on the left or on the right-hand side. This thing is set equal to 0, so I can still factor it and set each factor equal to 0. Right? No harm, no foul. Doesn't matter where the 0 is, one side or the other, as long as it's there. And now we're back in a situation where we've seen this, right? 2 cosine theta and a cosine theta to help me pick up 2 cosine squared theta for the first times the first. I need this -1, but I need a positive cosine of theta. There's a negative cosine theta. There's a positive 2 cosine theta, leaving me my cosine theta. And of course, yeah, the last times the last picks up the -1. So these are the 2 correct factors that I need. They create this expression on the right-hand side. Let's set each factor equal to 0 so that we can get a nice answer out of this. So either 2 cosine of theta minus 1 is 0, which tells me cosine of theta is add the 1, divide by 2, 1/2. Again, that happens in quadrants 1 and 4. So I'm looking at theta is going to be equal to pi over 3, or 5 pi over 3. The other one was cosine theta plus 1. That was my other factor. So let's take cosine theta plus 1 and set that other factor equal to 0. That means I'm trying to find where cosine of theta equals -1. Again, I jump to my unit circle. That's only going to happen at, and again, we're in radian, theta equals pi. Now, the question becomes, which of these answers are good? Again, remember back to this step where we squared both sides. We may be picking up a solution that really is not a solution, and we need to throw it in the trash. So what we need to do is check these answers. When we go back and we check our answers, it's best to go back to the very original equation, right? Because you've already messed with this, so if you messed something up, then you might plug your answer in and say, yeah, it works. Well, this wasn't what was given. This is what was given. So even though I've got some, pseudo solutions right now for theta, I don't know which of them work, and I don't know which one of them doesn't work, or if multiple don't work, or if all three don't work. Maybe when I squared both sides, I really got myself into trouble. So this is where we have to check. And again, we haven't had to do this before because we haven't had to square both sides. We haven't had to mess with that. So we haven't really needed to check. Now we definitely have to check. So let's go back and let's check theta equals pi over 3. All right, so if theta is equal to pi over 3, then I'm plugging in pi over 3 here, dividing by 2, minus cosine of pi over 3, and checking to see does that equal 0, right? I want to know if this thing is actually solving this equation. Well, if I have pi over 3 and divide by 2, I'm really multiplying by the reciprocal 1/2. Chop pi over 3 in half, you get pi over 6. All right, so is this really 0? Well, sine of pi over 6 is 1/2, minus cosine of pi over 3 is 1/2. Yeah, this one actually works out. 1/2 minus 1/2 is 0. So if this is a good solution, I'm going to keep that solution. Right, so I'll say theta equals pi over 3, but maybe 5 pi over 3 works as well. Let's try 5 pi over 3. Which means, again, back to the very original equation, sine of 5 pi over 3 needs to be divided in half, because it's a half angle, minus cosine of, I'm plugging in 5 pi over 3. Does that equal 0 is the question. So this is sine of 5 pi over 6. Right, it's a half angle, minus cosine of 5 pi over 3. Does that equal 0? Well, if we look at sine of 5 pi over 6, it's over there in quadrant 2, back it up, pi over 6, yeah, that is a half. If I look at cosine of 5 pi over 3, again, 5 pi over 3, I'm all the way over in quadrant 4, and that does give me positive 1/2. Cosine's positive in quadrant 4. There's a minus in between them. Yeah, basically getting the same thing I got before. This thing works. This thing is also 0. So I'll keep 5 pi over 3 as a good solution. Right, and at this point, you probably have one of two mindsets. You probably have, I'm getting pretty lazy. I'll trust that and say that's a solution as well, theta equals pi. Or you're in the other mindset that says, I bet you that one doesn't work, right? So flip your coin. No, don't do that. Check it, right? You always want to check it to make sure if it works or if it doesn't work, right? So let's plug in theta equals pi. We'll see if all three work. We'll keep all three. Or we'll see if we have to throw that one away in the trash. So I'm plugging in pi into my very original equation. And I want to see if it equals 0. The left-hand side, does it equal 0? Well, let's find out. Sine of pi over 2, straight up, that's 1. Minus cosine of pi, right, that's over at 180 degrees. At pi, it's negative 1. And I'm subtracting those two. I'm taking positive 1, and I'm subtracting negative 1. To me, this looks like ain't going to happen. 1 plus 1 equals 0. Nope, not going to happen. And so we are going to get rid of this. That goes in the trash. And these are our two good angles, pi over 3 and 5 pi over 3. So those are our only two solutions for the original equation there. So we had to be a little more careful with that one because of that half angle. We had to just watch out after we square both sides. We need to remember to go back and check to see if our answers actually make sense. And we have to do that every time we square both sides. Right? It's never a guarantee if you're going to get all good solutions, all bad solutions, which ones are the good ones, which ones are the bad ones. Obviously, with more practice, you could probably tell a little faster without having to write it down every step. But in the meantime, please, by all means, check all your answers just to make sure you're getting the right answers. So that's it. That's 6.2. And then the next section I'll cover is 6.3, which starts dealing with more multiple angles. We'll see a lot more of solving equations that have sine of 2x or sine of 3x or sine of 5x in them. And we'll see what happens when we get larger multiple angles involved within the argument of the trig equations. Again, let me know if you have any questions. I hope you're happy and healthy, and I'll see you in 6.3.